Okay, you guys, let's use the method of Lagrange multipliers to find the absolute extrema of f, where f is a 3-input variable function, and it's a constrained domain, right? The constraint is actually the surface, which is, in this case, a sphere given by x squared plus y squared plus z squared equals 12. So the idea is the domain is restricted. You're only allowed to plug in x, y, and z values that are on this sphere. Okay? And because this sphere is closed and bounded, you're guaranteed that the absolute extrema will exist. Hey, guess what? That's the absolute, or the extreme value theorem, isn't it? EVT, I like to call it. If your domain is a closed, bounded region, and your function is continuous, then you're guaranteed it will have an absolute max, absolute min on that domain. So I know it's going to exist because of that. Not because Lagrange multiplier says so, but because the extreme value theorem says so. So what do I do? Well, if you're taking the test and you're not sure what to do, you could always take some partials, right? I mean, it wouldn't hurt. But in this case, you're going to want to take some gradients, which do involve partials, right? Del f. Del f is the gradient of f. So let's do that. So what's the gradient of f? Well, you take the partial with respect to x. What's that? 4x cubed. And then that's the, remember the gradient, in this case, the gradient is going to be a space vector. If it's a 3-input function, the gradient's a space vector. If it's a 2-input function, the gradient is a vector in the plane. In this case, a space vector. So 4x cubed, the derivative with respect to x of f is the first component of del f. And then plus derivative with respect to y, 4y cubed, j, right? Plus 4z cubed, k. Everybody agree with that? So far, so good? All right, and then what do we do?
Find lambda gradient g.
Yeah, so what is g? So it's x squared plus y squared plus z squared minus 12. But had you thought of g of x, y, z as equaling just x squared plus y squared plus z squared, you'd still get the same partials. But it's just not quite right, and you have to be careful when this isn't a constant, then it matters. Okay, so set it equal to 0 every time, and then the side that's not equal to 0, that's what you call g. And then you take those partials, right? Del g. You could go ahead and throw in the lambda right now, lambda del g if you want, or take the partials and then multiply by lambda. What do you get?
Lambda 2x.
I'm going to say 2 lambda x just to be a rebel. I. But it doesn't matter, does it? You're right, I'm right.
Yeah.
Okay, and then plus derivative with respect to y times lambda.
2 lambda y.
2 lambda y, and then that's the j component. Plus 2 lambda z. And that's the k component. Method of Lagrange multipliers is pretty simple to state. It says that at extreme values, del f is equal to lambda del g. Since those are both vectors, that means you can set corresponding components equal, and you got yourself a system of equations such that when you solve that system, you get your critical points. And then if the absolute extrema exists, you plug those critical points back into f. The biggest value that you get when you plug into f is your absolute max. The smallest one is your absolute min. So it's pretty simple to state. What's the problem? The problem is actually solving the system you get, right? It can be quite complicated. Okay, so that's what we'll work on. There we go. So let's create that system right now. So what's the system then? 4x cubed is equal to 2 lambda x, right? So in other words, I'm setting corresponding components equal. What else should I write down with my system? This is a system of equations I've just created. The constraint is also one of those equations that must be satisfied, right? And you need that. I'll write down the first version of the constraint, the sphere x squared plus y squared plus z squared equals 12. X squared plus y squared plus z squared is equal to 12. Okay, so this is your system. The problem is it's nonlinear. So when you have a linear system of equations, it's a step-by-step process to solve it. It's not necessarily easy. Well, it's easy to make a mistake, but it's not hard to solve it conceptually. Here, you know, what do you do? Do you solve for lambda? Do you solve for x? What do you do? You don't know. It depends on the problem. Okay, so one way to approach this is I do notice we've got a lot of nice symmetry here in the first three equations. And it does turn out, okay, there's two ways to approach this. You could factor the equations. Okay, so I'll give you, I'm going to erase this, but I want to give you this option. If you want to factor so that you don't lose anything, then you could set each of these first three equations equal to 0, like so for the first equation. And then couldn't you factor out, what could you factor out of this first equation on the left side? A 2x, and then what's left? 2x squared minus lambda. And then that's equal to 0, right? So that gives you two possibilities. Either 2x equals 0, or what? Lambda equals 2x squared? Or x squared, you know, it depends on how you want to solve it, but 2x squared equals lambda, and you can solve it as you want from there. So this is like one case, and this is another case. And the thing is, you get similar things happening for y and z when you solve this equation and this equation, right? So the thing that makes this problem difficult is all the different possibilities. Well, that's why I said I'm going to erase this. I don't quite like doing it this way. But you do have to remember, it is possible x could be 0. So keep that in mind as I show you the way I like to actually work this problem. So if you would rather work it this way, go for it. If you'd rather factor, go for it. But let me contrast it with another way. So let me assume that x, y, and z don't equal 0 for now. But I eventually have to go back and look at what happens when 1 or more does equal 0. You can't just throw that away, that possibility. Okay? And the good thing about factoring is it helps you not forget that possibility. So, okay, so let's, if first of all, I'm going to assume none of the variables equal 0. X, y, z, none of them equal 0. If that's the case, can't I greatly simplify these equations? I could divide out a 2 and an x in the first equation, right? What does that leave me with? So 2x squared equals lambda. And I'm just, to be very pedantic about it, I'm going to write it down again. This is assuming x does not equal 0. Why is that so important? Because I just divided out an x. Am I allowed to divide by 0 if x is 0? No, I'm not. So I have to separately look at the case when x equals 0. And I want to make that clear. Because if you don't look at that, you're going to lose. I think you end up losing your maximum value in this case. All right, so now let me do something similar for the other two equations. What do I get? Divide by 2 lambda, or 2y actually in this second equation. What do you get? 2y squared equals lambda. Isn't that nice? And then what do I get for the third equation? 2z squared equals lambda. Now, what's the assumption in these second two equations? In the second equation, y does not equal 0, right? And I'm writing it down so that I don't forget to go back and see what happens when y can equal 0. And same thing here. So I'm going to see what happens when none of them are 0, and then I'll go back and check when 1 or more is 0. Okay? So that's what's so easy to forget when you're new at solving these. Yeah, okay, you got to look at all the cases where they do equal 0 and when they don't. Okay. So this is really nice because if you look at the third equation then, oh, it's all in terms of x squared, y squared, and z squared, right? So what do we get then from these equations? How could we get it in each? Well, how do you want to do it? You want to get everything in terms of? You mean x squared or x? X squared, yeah, okay. So, yeah, so what does that mean? That means this equation here, well, you can't see it in the video, but this equation here means that x squared equals lambda over 2, right? So x squared equals, whoops, x squared equals lambda over 2. Well, let's put it all at once. Aren't all of them equal to lambda over 2? X squared equals y squared equals z squared, which is lambda over 2. So what can we do then from here? What, do we need to bother plugging in lambda over 2? Can't we just say that they're all equal to each other? So another way to approach it, maybe one that would make more sense, is since all of these are equal to lambda, they're equal to each other, right? So maybe, yeah, okay. Well, that's okay. So I could have put it this way. I could have said 2x squared equals 2y squared equals 2z squared, which means x squared equals y squared equals z squared. Okay, so I'll erase that other part, otherwise it's confusing. Is that clear? Okay. Yeah, you fiddle around with it until you get it right. Now, if they're all equal, then it doesn't matter which variable you call all of them. Just we could call them all of these x's, right? Y we could call x, z we could call x, and then we get from the last equation x squared plus x squared plus x squared equals 12. Or 3x squared equals 12. Or x squared equals 4, or x equals plus or minus 2. Yeah? But doesn't that mean that y equals plus or minus 2 and z equals plus or minus 2? Yeah. Now here's the problem, you guys. I can't write my critical points as plus or minus 2, comma, plus or minus 2, comma, plus or minus 2. You guys see why? Because that kind of indicates there's only 2 critical points. There's actually critical points with any combinations of pluses and minuses, right? Now, you can take all those into account fairly easily if you just leave the plus or minus on one of them and then mix and match the plus and minuses on the other. So here's one critical point. There should be how many altogether? 8, right? 8. So here's 2 of them actually, right? Because of the plus or minus. So what's another one? Plus or minus 2, I don't know, negative 2, 2. That's 4 altogether, right? And then plus or minus 2, negative 2, negative 2. That would be 6 altogether. What am I forgetting? Plus or minus 2, 2, negative 2. 2 each, that would make 8 of them. Okay. Now, in this case, it doesn't really matter, does it? Because if you plug any one of these into the function, remember what the function is originally, way up here, you're going to end up taking each one to the 4th power, and the negative is going to go away anyway. So you're going to get the same value of f for each one of these critical points. Okay. So you could find that now. You could find it at the end. It doesn't really matter. So we'll find the value of these critical points at the end of the problem, I guess. Okay, so what possibility haven't we looked at yet then? Well, what happens when x equals 0? But we can be a little bit more general here. You're going to get the same answer when x equals 0 or y equals 0 or z equals 0 and the other two are non-zero. Okay? So you could say this. Suppose one of x, y, or z, 1 is equal to 0. Then the others equal what? Well, these equations are still valid for the other two. So let's suppose x equals 0, just for the sake of argument. And the argument would go the same way if y or z were equal to 0. But just to grab a hold of something, let's say x were equal to 0. Then these two equations are still valid. This one's not, right? If x equals 0. Because how did we get this equation? We got this equation by dividing this equation by 0. No, by x. But we can't divide by 0 when x is 0. So this one is no longer valid if x does, in fact, equal 0. But these two are still valid. And they say that the other two variables are still equal, right? Yeah. So I'm trying to be more general here. Then the others are equal. Then the others are equal. Okay, because those equations above still hold. Well, okay. So if the others are equal, that means we can still use this third equation. It's just one of the x squared or y squared or z squared is gone. So let's do this. For the sake of argument, this is going to help you understand. Let x equal 0. Then, by what we just talked about, y squared rather, and z squared are equal. Okay? But that means that y squared plus y squared is equal to 12, right? From that bottom equation, you plug in x equals 0 and z equals y. You get y squared plus y squared is equal to 12. Or 2y squared equals 12. Or y squared equals 6, which means y is equal to plus or minus root 6, which means z is equal to plus or minus root 6. But do you guys see by the nature of the function and by the constraint that if one of the variables is 0, the other two are plus or minus root 6 in any combination of pluses and minuses? So why write it all down? Why not just say it in English? This is one of the few times where saying it in English is easier than writing down all the possibilities. So that's what I'm going to do. So I'll say in general, and this is just by the nature of the symmetry of the two functions. It wouldn't be true with every problem. With other problems, you might have to write them all down because you might get different values when you plug them in to find when you plug in your critical points into the function. But here you won't. So in general, if x or y or z equals 0, the other two are plus or minus root 6 in any combination of pluses and minuses, right? Okay. So those are my critical points. I'm not going to specifically list them. I'm just going to say this statement gives me my critical points. Now, don't get me wrong. On the test, the problem is going to be such that you should be able to list the critical points. Okay? It won't be as complicated as this one. But if you can get this problem, you can get the one I give you on the test. Okay. So is that clear? So this gives you, it's supposed to be R right there. This gives you your critical points in that situation. Now, there's one other situation we haven't looked at. What if two of the x, y, or z are equal to 0? So the last situation, two variables are 0. So I'll put a colon there. Two variables are 0. Without loss of generality, or for the sake of argument, let's let x and y equal 0, just to see how it goes. If x and y are equal to 0, then from that last equation in our system, if x is 0 and y is 0, then we get z squared equals 12, right? Yeah. So then you could say then z squared equals 12, or z equals plus or minus root 12. So I'll say this. So in general, if two variables are 0, the other is plus or minus root 12. Make sense? There's actually not that many of them in that situation, right? You could list them all if you wanted to. Okay, so let's list all the function values from these critical values we've come up with. I'll say this. If x, y, z, notice I put comma, are plus or minus 2. I'm not saying they're all equal. Some could be plus, some could be minus. Then f of x, y, z, what's that going to be? It's going to be, well, 2 to the 4th plus 2 to the 4th plus 2 to the 4th, or 48. Is that clear? So, okay, so we got to look at that. Is that going to be a minimum, a maximum? Well, we don't know yet. If one variable is 0, comma, then f is going to be, well, we know the other two are what? If we, I skipped it, sorry. Yeah. Then the other two are plus or minus root 6, right? So you end up with, I'm going to be very non-specific here because all I really care about is the function value. You end up with f equals 0 to the 4th plus or minus root 6 to the 4th. The minus goes away. The minus goes away when you take it to an even power. And what do you get, 72? 72. Is that clear? So circle that. Is that going to be the max? I don't know. There's one more possibility. If two variables are 0, then what's the function value? You end up plugging in plus or minus root 12 for either x, y, or z, and the other two are 0, right? So you take plus or minus root 12 to the 4th power. So f equals, the minus goes away, and I think that's going to be 144, isn't it? That's your absolute max, isn't it? And then your absolute min turned out to be 48. Okay? Now, don't panic. This was not meant to be a test problem. It was meant to be a homework problem. Okay? You don't have time to do this long of a problem on a test. But the point is, you practice problems that are harder than will be on the test, and the test seems like nothing. And I love this problem because it makes you think. And you need to take into account all these different possibilities. Okay? So be able to work this problem, but don't stress. I'm not going to put this one on the test. It could be one similar, or it could be a stripped down version of this problem, where I ask you to just look at a particular situation where some of these other possibilities aren't there anymore.